How does entropy affect heat engines? Have you ever wondered why some engines seem to perform better than others? The secret often lies in a concept called entropy. Entropy measures disorder in a system and plays a key role in how heat engines operate. Let's break this down. Heat engines take heat energy from a high-temperature source and convert it into useful work. However, they also have to reject some heat to a low-temperature sink. This process is governed by the second law of thermodynamics, which tells us that the total entropy of an isolated system can never decrease. It can only increase or stay the same in ideal situations. This principle sets limits on how well heat engines can perform. At the heart of this discussion is the Carnot cycle. This is an idealized engine cycle that operates between two temperature reservoirs. It assumes no entropy generation, meaning it represents the best possible efficiency any real engine can achieve. The efficiency of this cycle depends solely on the temperatures of the hot and cold reservoirs. If any engine were to operate with less entropy generation than the Carnot engine, it would contradict the second law, which is impossible. In real engines, entropy generation occurs due to various factors. Friction, unrestrained expansions, heat losses, and finite rate heat transfer all contribute to this. As a result, the actual efficiency of a heat engine is always lower than the ideal limit set by the Carnot cycle. During the heat addition phase, entropy increases as heat flows from the high-temperature source to the working fluid. When heat is rejected, entropy increases again as heat is expelled to the low-temperature sink. Over a complete cycle, the net change in entropy is positive, which reflects the irreversibilities present in real engines. This increase in entropy indicates energy that cannot be converted into work and is instead lost as waste heat. Furthermore, some heat must always be rejected to the cold reservoir. This is necessary for the working fluid to return to its initial state, which is essential for maintaining a cyclic process. The disposal of the gained entropy during heat absorption is unavoidable. From a mechanical engineering perspective, understanding entropy is vital for designing more efficient heat engines. Engineers aim to minimize entropy generation by reducing friction, optimizing combustion, and improving heat exchanger effectiveness. They also focus on controlling expansion and compression processes to get as close to reversible conditions as possible. Advanced thermodynamic models often include entropy analysis to evaluate and enhance engine cycles like Brayton, Rankine, and Stirling engines. In essence, entropy plays a fundamental role in determining the efficiency of heat engines. It quantifies the irreversibility and waste energy that engineers must consider when analyzing, designing, and optimizing these machines for better performance and reduced energy losses.